Hi, everybody. Let's see again, and let's start our lecture number 17. Okay, nice. This is our course on sensors and instrumentations. And during today's lecture, we will be continuing the previous topic, performance specification and rating parameters. And the first topic of today's lecture is called gain margin and phase margin. You know, gain margin and phase margin are measures of stability of device. To define these two parameters, consider the feedback system of this figure. The forward transfer function of the system is G from F. And the feedback transfer function is H from S. S here is a J times omega. These transfer functions are frequency domain representations of the overall system, which may include a variety of components such as plant, sensors, transducers, actuators, controllers, and interface, and certainly signal modification device. The body diagram of the system constitutes the magnitude and phase slate plot of the loop transfer function G times H as a function of frequency. This is sketched in this slide. Suppose that at a particular frequency omega, the forward transfer function G in the upper line provides a phase lag of psi1, and feedback transfer function H provides a phase lag of psi2. Now, in view of the negative feedback, the feedback signal undergoes a further phase lag of phi, and hence the total phase lag in the loop equals psi plus phi, where phase lag of G times H equals psi1 plus psi2 and equals simply psi. It follows that when the overall phase lag of the loop transfer function G times H is equal to pi, the loop phase lag becomes 2 pi, which means that if a signal of frequency omega travels through the system loop, it will not experience a net phase lag. Additionally, if at this particular frequency, the loop gain G times A is unity, a sinusoidal signal with this frequency will be able to repeatedly travel through the loop without ever changing its phase or altering its magnitude, even in the absence of any external excitation. This corresponds to a condition of marginally stability. If, on the other hand, the loop gains G times H in absolute value, as you can see in this one, is a positive one in second axis. At this frequency, while the loop phase lag is pi, the signal magnitude will monotonically grow as the signal travels through the loop. And this is unstable situation. On the other hand, if the loop gain is less than 1, at this frequency, while the loop phase lag is pi, no matter which sign we have, the signal magnitude will monotonically decay as the signal cycles through the loop. And this is a stable situation. So in summary, we may found as a 3 situation here. First, when loop gain is equal 1, then the system is marginally stable. And to another, when we already just explained, when loop gain more than one, because the system is stable, and opposite, when the loop gain is less than one, the system is stable. Sorry, first is unstable. So it follows that the margin of smallness g times h, when compared to 1 at the frequency omega, where angle between g and h is minus pi, provides a measure of stability. This is term gain margin, as you can see from this slide. And similarly, at the frequency omega, where log equals 1, the amount of margin of phase log that can be added to the system, so as to make the loop phase log equal to pi, is a measure of stability. Okay? Okay, let's go. This amount is term phase margin. In terms of frequency domain specification, a device such as a transducer, an amplifier, or a sensor system should have a wide useful frequency range. For this, it must have a high fundamental nature of frequency, about 5-10 times the maximum frequency of the operating range, and somewhat low damping ratio, slightly less than 1. The transfer function h for a simple oscillator is given by these first equations. The frequency function h is proportional to y over u. And where the h from s here is a combination j times omega. Yes, we can see here on the bottom. Omega here is excitation frequency, right? We should notice that h from j omega is a complex function of omega. We have that the gain of h is a magnitude of h. And phase lead is a phase angle between h and j ohms. This represents amplitude gain and phase lead of the output or response when a single input signal or excitation or frequency omega is applied to the system, right? Resonant frequency omega r corresponds to the excitation frequency when the amplitude gain is the maximum and given as this one. So omega resonance is the equal square root from 1 minus 2 psi squared and times omega natural. This concept is used to measure the damping in a device, in addition to specifying the performance in the frequency domain. But note, the first order model has the frequency response function, as you may see here for h as a j omega. It is clear that this model has only one performance parameter, namely time constant tau, right? Since the gain k can be normalized to 1 and adjusted physically by an amplifier or computationally by simply multiplying the response by a constant. And further, it cannot represent an undamped system, and hence a condition of resonance. In particular, a simple oscillator model cannot be obtained by cascading two first-order models. A popular method of linearization of nonlinear devices considers a local behavior over a small operating range. This local linearization is straightforward, but is not generally applicable due to such reasons as follows. First, the operating conditions can change considerably, and single local slope may not be valid over the entire range. Second, the local slope may not exist or insignificant compared to the O. And in some nonlinear systems, the use of local slope, like negative damping in a control law, may lead to undesirable consequences or instability. So, several other methods are available to reduce or even eliminate nonlinear behavior in devices. They include the use of calibration curves in the static case, linearizing elements like resistors and amplifiers in bridge circuit to neutralize the nonlinear effect. And nonlinear feedback is a significant consequence of a static nonlinearity is a distortion of the output. This can be linearized by recalibration or rescaling. For example, suppose that the input U minus input Y behavior of a device is given Y proportional k times E in power PU. It is clear that a sinusoidal unit U equals U naught times sine omega t will be far from sinusoidal at the output, and we can see in the first diagram here. And clearly, we can transform the problem as a logarithm y should be equal p times u plus logarithm k. And hence, the input-output relationship can be accurately linearized by simply using a logarithm scale for the output, and also adding a constant offset as a minus logarithm k. So it's a line we can see, logarithmic line. And nonlinear output became is the first one. To illustrate this, let us use the parameter value. And in this recalibrating form, the output for a sinusoidal input will be purely sinusoidal. So let's use the parameter values for k equal 2, p equal 1.5, u naught 2, and omega 1. We use the following MATLAB function to determine the input-output behavior at the upper figure, and corresponding to signals we have in the bottom figure here. It is seen that the actual nonlinear function considerably distort the sine signal while using a logarithm scale for the output, and can conventionally and accurately linearize the behavior, giving an undistorted output. And furthermore, with the logarithm output shown in upper figure, we can extract the two parameters p and k from the slope and the y-intercept of the linear curve. Specifically, p or slope equal 3/2 get us 1.5, and logarithm k for 0.7 get us k equals 2. For mitigating nonlinearity problems, it is a good practice to take such precautions as the following. First, avoid operating the device over a wide range of signal levels for input, and avoid operation over a wide frequency band. Use devices that do not generate large mechanical emotions. Minimize Coulomb friction and stiction. Avoid loose joints and gear coupling. Minimize environmental influences and sensitivity to undesirable influences, and certainly minimize wear and tear. And let's come to the next subtopic of today's lecture, as called called instrument rating. You know, instrument manufacturers do not usually provide complete dynamic information for their product. In most cases, for practical engineering systems and complex instruments, it is unrealistic to expect complete dynamic model in the time domain or the frequency domain, and accurate parameters values for the model. Performance characteristics provided by manufacturers and vendors are primary static parameters, known as instrument ratings. These are available as parameter values, tables, charts, calibration curves, and empirical equations. Dynamic characteristics such as transfer functions might also be provided for more sophisticated instruments. But the available dynamic information, is never complete. The rationale for this is that under the normal operation conditions of a typical device, like sensors, amplifiers, data acquisition hardware, the device dynamics should have a minimal effect on its output. But nevertheless, some information on the dynamics of the device, like time constants, bandwidth, would be useful in selecting the operating conditions and components for a practical application. Definitions of rating parameters are used by manufacturers and vendors of instruments, are in some cases not the same as the analytical definitions used in tests. And this is particularly true in relation to the terms linearity and stability. Still, instrument ratings provided by manufacturers and vendors are very useful in the selection, installation, and interconnection, certainly in operation, control, and maintenance of components, and in engineering systems. Let us examine the key performance parameters. Typical rating parameters provided by instrument manufacturers and vendors in their data sheet are the following, and you can see on this slide. It's sensitivity and sensing and sensitivity error, signal to noise ratio SNR, dynamic range DR, resolution, offset or bias, linearity, zero drift, full scale drift, and calibration drift for stability. Useful frequency range, bandwidth, and certainly input and output impedance. We have already discussed the meaning and significance of some of these terms. In this section, we examine the conventional definitions for rating parameters as given by instrument manufacturers and vendors. So let's start with sensitivity. The sensitivity of a device or transducer is measured by the magnitude, peak, Roman square value, and tensor of the output signal correspondingly to the unit input or measurable, right? These may be expressed as the ratio of incremental output and incremental input, like slope of input-output curve of the device, or analytically as the corresponding partial derivative in the input-output relationship. It is clear that sensitivity is also the gain of the device. In the case of vectorial or tensorial signals, like displacement, velocity, acceleration, strain, or force, the direction of sensitivity should be specified. A countless number of factors, including environment, can affect the output of a device such as that. And then the important objectives of instrumentation with respect to sensitivity would be the following. And you can see this on this slide. Select a reasonable number of factors that have noteworthy sensitivity level on the device output. Determine the sensitivities of the selected factor. Maximize the sensitivity to desirable factors and minimize the sensitivity to undesirable factors or cross-sensitivity. Let's describe a bit more details about cross-sensitivity. Cross-sensitivity, this is a sensitivity along directions that are orthogonal to the primary direction of sensitivity. It is normally expressed as a percentage of direct sensitivity. High direct sensitivity and low cross sensitivity are desirable in any input-output device or measuring instrument. Sensitivity to parameter changes and noise has to be small in angle. However, and this is an indication of its robustness. On the other hand, in adaptive control and self-tuning control, the sensitivity of the system to control parameters has to be sufficiently high. And often sensitivity and robustness are conflicting requirements. Digital devices generate digital output. They include devices that generate pulses of count, or those with built-in analog to digital converter, ADC. Sensitivity of any digital device can be represented in the usual manner. Specifically, as this in this expression, sensitivity proportional digital output and inverse proportional for corresponding input. More commonly, the input is analog, but digital input can be accommodated in the same definition. An n-bit device can represent two n values, including 0. Then, the maximum possible value for unsigned is 2n minus 1. To represent signed value, we need to assign one bit as a signed bit. And then, n-bit device can represent 2n minus 1 positive values, including 0, and the same number of corresponding negative values, right? Another way of interpreting a digital output is as a count. Indeed, the actual output of device may be a count of pulses or events. Then an n-bit device can represent a maximum 2n count because 0 and the sign are not relevant now. Are you agree with me? Nice. If we use this latter approach, the digital sensitivity of a device may be expressed as, let's look at this expression, 2 in power n over full scale input times in count per unit input. For example, suppose that a potentiometric displacement sensor gives an output of typical 1.5 volt for a displacement of 5 centimeters. If the power supply of the potentiometer or its reference voltage is 10 volts, then the sensitivity of the device may be given as, you remember, 1.5 divided by 5 divided by 10, right? And we get a 30 millivolt over centimeter over volt. Some examples of sensor sensitivities are given in this table on the bottom. Okay. Let's look at this example. Suppose we have a photovoltaic light sensor that can detect a maximum of 20 lux of light and generate a corresponding voltage of 5 volts. The device has an 8-bit ADC which gives its maximum count for the full-scale input for 5 volts. What is the overall sensitivity of the device? Let's start our solution. The maximum count of the ADC is 28. Sorry, 2 in 4 power 8. It gets us 256 count, right? And this corresponds to 5 volts into the ADC, which is the sensor output for the maximum possible light level of 20 lux. Hence, the overall sensitivity of the device is 256 over 20, get us 12.8 counts per lux. But no, the sensitivity of the ADC alone is 256 over 5 counts per lux, per volt, sorry, and get us 51.2 counts, not per lux, counts per volt. Okay? The rated sensitivity of a device, as given in its data sheet, may not be accurate. It's typical. The difference between the rated sensitivity and the actual sensitivity is called the sensitivity error. The sensitivity, which is the slope of the input-output curve of a device, may not be accurate for reasons such as, first of all, its effect of cross sensitivities of undesirable input. And next, drifting due to the wear and environmental effects, or dependence on the value of the input. This means the slope changes with the input value, and it is a reflection of the nonlinearity in the device. Next is the local slope of the input-output curve. Concerning last item number 4 in this list, the local slope or derivative may be 0, or maybe infinity, or may be less significant than the higher derivative term of the Taylor series expansion. Then, either a local sensitivity cannot be defined, or a local sensitivity is not significant. In such situation, a global sensitivity may be used. Error in sensitivity may be represented using a plus-minus range of variation of the average sensitivity, which corresponds to the difference between the minimum and maximum values, which the actual sensitivity may vary. And this total variation of the sensitivity, maximum minus minimum, is a measure of the static nonlinearity of the device. As mentioned earlier, the sensitivity in instrumentation may be handled as either a design issue or a control issue. In particular, the main objective being maximization of the sensitivity for undesirable factors. It may be achieved through both design and control. Once a system is designed for the sensitivity objective, it may be further improved, or specific sensitivity objectives may be achieved through through control. Sorry, it's not that slide I want to show you. It's a bit different. I want to show this one. Yeah. So the accuracy of a control system is affected by parameter changes in the system component. and by influence of external disturbances. And furthermore, some types of control, like adaptive control, self-tuning control, depend on the sensitivity of the system to control parameters. It follows that analyzing the sensitivity of a feedback control system to parameter changes and to external disturbances is important. Consider the block diagram of a typical feedback control shown in Figure A on the middle of this slide. Consider in the usual notation, we have G sub P as a plant or control system, and transfer function G sub C as a controller, including compensator and other hardware transfer function. H is the feedback, including measurement system, transfer function U, and you set on the left side here as the system command, and Y in opposite side as the system output, and UD as the external disturbance system. For linear system, the principle of superposition applies. In particular, if you know the output corresponding to two inputs, when applied separately, the output when both inputs are applied simultaneously is given by sum of the individual outputs, right? So we use this principle here too. First, set the UD equals 0, and then it is straightforward to obtain the input-output relationship. So let's look this expression here for Y. Okay, so next, set U equals 0. Then we obtain the following input-output relationship, as we can see here on the top of this slide. And by applying the principle of superposition, we obtain the overall input-output relationship, and we can get our next expression here for U and from U disturbance. The closed loop transfer function is G tilde is given by Y over U with UD equals 0, and thus let's get this very nice loop expression. System sensitivity to parameter change. The sensitivity of the system to a change in some parameter K may be expressed as a ratio of a change in the system output to change in the parameter. No, like delta Y over delta K. In the non-dimensional form, this sensitivity is given by these simple expressions. S sub K, it's K over Y times delta Y over delta K. But no, the non-dimensional form on sensitivity is generally suitable because it enables a fair comparison of different sensitivities. Since Y proportional G tilde times U with UD equals 0, it follows that for a given input U, and we can get the expression for Sk, or in the limit, as you can see, as this last expression here on the bottom. K over G tilde times the partial differential from dg tilde over d partial differential K. Now, by applying last two equations, we are able to determine expression for the control system sensitivity to changes in various components in the control system. Specifically, by straightforward partial differentiation of equation before last, separately with respect to GP, GC, and H. Respectively, we get these three equations. It is clear from these three relations that as the static gain or DC gain of the loop is increased, the sensitivity of the control system to changes in the plant and the controller decreases, but the sensitivity to changes in the feedback or measurement system approaches negative unity. And furthermore, it is clear from this equation on previous slide, I just for a second show you, that the effect of the disturbance input can be reduced by increasing the static of gain G, C, and H. G, C, and H. G, C, and H. By combining these observations, the following design criteria concerning sensitivity can be stipulated for a feedback control system. Make the measurement system H robust, stable, and very accurate. Increase the loop gain to reduce the sensitivity of the control system to changes in the plant and control. And increase the gain of G sub C times H to reduce the influence of the external disturbances. In practical situations, the plant G sub P is usually fixed and cannot be modified. And furthermore, once a suitable and accurate measurement system is chosen, H is exceptionally fixed. And hence, most of the design freedom is available with respect to G sub C only. It is virtually impossible to achieve all the design requirements simply by increasing the gain of G sub C. The dynamic of G sub C, not just the gain value at S equals 0, also have to be properly designed in order to obtain the desired performance in a control system. And now let's start our summary sheet. Performance specification. It's the parameters. There are parameters that are used to indicate the rated or expected performance of a device. Categories of performance specification. And these are error, speed of performance, and stability. Type of performance parameters. First, it's parameters used in engineering practice, provided by device manufacturers and vendors. And second, parameters defined using engineering theoretical considerations, like model-based. Models used for performance specification. First, it's differential equation model for time domain. And second, transfer function model for frequency domain are two types of dynamic models that are used for performance specification in the analytical domain. And last, perfect measurement device. The main characteristics of a perfect measuring device are, first, its output instantly reaches the measured value, like fast response, zero error, and second, the output level is high. Third, the output remains steady at measured values when the measurand is steady. And fourth, the output varies in proportion to the measurand for static linearity. 5, the device does not distort the measurand. When we have a loading effect or matched impedances. And 6, it is accurate, acquires low power consumption for high input impedance. And now we will start another topic of today's lecture. It's called estimation from measurement. And first subtopic of this lecture called sensing and estimation. In the use of a sensor system, the measured quantity may be a constant parameter, like moment of inertia, of a length of a robot arm, an average property of a batch of items, like average internal diameter and its variance of a batch of ball bearing. A varying parameters like resistance of a strain gauge as the temperature changes, or a process variable like velocity of a vehicle. The sensor measurement may not provide the true value of the required parameter or variable for two main reasons. First, what is measured may not be the required quantity and will have to be computed from the measured value using a suitable model. And second, the sensor or even the sensing process is not perfect and will introduce measurement error. Hence, sensing may be viewed as a problem of estimation, where the true value of the measured quantity is estimated using the measured data. Clearly, two main categories of errors, model error and measurement error, enter into the process of estimation and will affect the accuracy of the result. The underlying concept is schematically shown in this figure. The process model is shown here as a function Ft from theta. Theta is a quantity, which is to be measured. In some situations, this function may be nonlinear and dynamic, or not an algebraic function, but a differential equation. And it may also include unknown and random effects. In other words, there can be model error. So in this figure, the measurement is shown as a function as the f from m sub m from theta of the measured quantity theta. And this function may also be nonlinear and dynamic due to sensor dynamics, and may include unknown and random effects like sensor noise and errors in the measurement process in general. In other words, the measurement may be neither direct nor exact. The estimator generates an estimate Q hat and measurement data Fm from theta according to some model. Since the information will not be exact or complete, the estimate will not be precise. An optimal estimator will determine the best estimate according to some criteria like least square error. Many methods of parameter estimation are used in sensing. Some methods use all the measured data simultaneously as a batch to estimate the required quantity. This is a non-recursive approach. Other methods use the measured data as they are generated and update or improve the current result at each sensing step. In other words, the current estimate and the new data are used to compute a new estimate at each sensing step. This is a recursive approach. For example, Kalman filter is a recursive approach for parameter estimation, and it explicitly addresses both model error and measurement error to arrive at an estimate that is optimal, one that minimizes the square error. Clearly, if the measured quantity itself changes with time, one has to use a recursive or time-varying approach of parameter estimation. In our lecture, we will learn a last square estimation, LSE, maximum likelihood estimation, MLE, and four versions of Kalman filter, namely scalar static Kalman filter, linear multi-variable dynamic Kalman filter, extended Kalman filter, EKF, which is applicable in nonlinear situations, and uncentered Kalman filter, UKF, which is also applicable in nonlinear situations and has advanced over the EKF, or extended Kalman filter, because it directly takes into account the propagation of random characteristics through system nonlinearity. Now, we came to the next subtopic of today's lecture, called least squares estimation. In the least square estimation, or LSE, we estimate the unknown parameters by minimizing the sum or squared error, SSE, between the data and the model of the data. And hence, this is an optimal method of estimation. The unknown parameters are the model parameters. If the model is linear, we have linear LSE. If the model is nonlinear, we have nonlinear LSE. Yes, very simple. In least squares point estimation, an unknown constant parameter is estimated using a batch of measurements, certainly with error of the parameter, such that the SSE between the data set and the estimated value is minimized. Suppose that the value of a constant parameter, like mass, is to be estimated by using data from several repeated measurements. A reasonable estimate of the parameter would be the average value of the data set or batch operation. It can be shown that this is also the optimal estimate in the sense of least square. But note, this approach is applicable to repeated measurement of the same parameter, of the same object, and measurement of a particular parameter in each object of a batch of objects that are nominally identical. To show this, suppose that a constant parameter of unknown value m is repeatedly measured using a sensor and n capital time, so that we may measure from n capital time. To generate the data set y1, 2, 3, up to y sub n. Note, as traditionally done, we use the uppercase y represent to the data in order to emphasize the fact that it contains random elements. The SSE in the data set is, you can see here for this expression, right? To find the value of m, in other say, the estimate m hat of the unknown constant m that would minimize the square error or produce the least square error, we differentiate E with respect to VR and equate the result to 0, and as we can see here on the right side of this talk. So we get the third equation for our m hat here on the middle of the slide. M hat, it's a 1 over n times as a sum for all y generate data set from 1 to n. This result indicates that the least squares point estimate, an optimal estimate, is the sample mean of the data. Assuming that this model is correct, the only error that is present is the measurement error. Alternatively, both model error and measurement error may be integrated into a single error parameter, albeit without having the capability to distinguish between the two. But more, the measurement error can come from both the sensor and measurement process. And clearly, the error will affect the accuracy of estimate given by this equation. The estimation is a batch operation where the entire data set is used to bundle. And hence, it has to be performed offline. And this operation may be converted into a recursive scan, which can be executed online as the data are measured. As follows, you may see equations here for M1 hat and M hat from I plus 1, this expression. We expect the accuracy of the estimate to increase as more data come in, assuming that the measured or estimated quantity in a constant and the error in random. In addition to the randomness in the measurement process, including sensor, the analytical representation of the measured or estimated quantity itself contains some random components. Specifically, there is a randomness in the model. The model may include the relationship between the measured quantity and estimated quantity in addition to analytical representation of the process or system that generates the data. To illustrate the related concepts, consider a high-precision manufacturing process where ball bearings are produced according to a tie tolerance at the nanometer level. In particular, the roughness of the bearing balls is an important parameter of quality control of ball bearing. For this purpose, suppose that a simple bearing ball of a specific nominal diameter, required size, is randomly chosen from a manufactured batch, and the diameter of each ball is measured using a roundness probe. A typical roundness sensing system is sketched in this slide. The sensing device has a turnable on which a ball would be mounted. A probe comes into the contact with the ball, and a servo mechanism in the device ensures that the contact with the ball is maintained continuously. As the turnable rotates, the probe moves according to the outer profile of the ball. And the probe moves in sensing using a differential transformer and recorder. The maximum deviation of the ball diameter is measured in this manner. For such a sensing system, a typical sensor accuracy is plus minus 25 nanometers, and the typical sensor resolution is only 5 nanometers. In this measurement process, a simple set of balls is chosen randomly, and each ball in the sample that is measured is also chosen randomly in sequence. And furthermore, due to the random effect in the manufacturing process, the actual ball diameter also changes randomly, albeit within some tolerance limit which covers acceptable production quality. It follows that there is randomness is the data for each ball due to the following causes. First, manufacturing process of each ball. Second, selection of the sample set of balls from the produced batch. Third, selection of a ball from a sample set. Fourth, ball mounting and probe contact in the roughness measuring device. And fifth, error in the probe or sensor. Item 1 for manufacturing process of each ball introduces randomness into the process model itself, and it directly affects the product quality. Item 2 through 5, that's from selection of the sample set of balls up to the error in the probe, all corresponds to the randomness in the measuring process, which indirectly affects the product quality by producing an accurate estimate of the actual roundness. Consider a set of measurement data, y1, y2, y3, and up to y sub n. And since the goal of the measuring process in the present application is to determine the quality of the produced bearing ball, suppose that the model that is used for this purpose consists of two quantities. First, the sample mean is defined as these equations. Average y proportions y over n quantities and sum from each component. And second, the sample variance is defined as these equations here. Square root c, square from c, 1 over n minus 1, and sum from each deviation from every y minus average square. These two quantities are known to be unbiased estimate. Specifically, the expected value of the sample mean equal the true mean, and the expected value of sample variance at the bottom is equal for the true variance sigma squared. And hence, assume that the measurement y sub I, it will be ended random variables of mean value mu and variance sigma squared. Right? Then it can be shown that the expected values of the two estimates are equal to the mean and variance of the measurement. That is, look at the last two equations. As we observed earlier, in the present situation, the randomness of the measured data comes from both model randomness and measurement randomness. 5 types were listed a bit earlier. However, in the present method of estimation, these various types of contributions are not treated separately and are represented in the integrated manner. It should be emphasized that the randomness is in the signal of the random process and not in the parameters that describe that random process, like mean, mu, and square root sigma. Furthermore, the data measured from a random process are also random. And hence, the estimates that are computed from the data are also random. Let's look for this example. We have a roundness sensor produced the following set of diameter measurements in millimeters for a sample of 10 bearing balls from a production batch. And you can see this line as X. .5, .1, .2, and all of this stuff. To process the data, we define the MATLAB function subm using the script given by the following m file, as you may see here at the slide. We may treat the sample mean equal as a 4.997 millimeters as an estimate of the diameter of the batch of ball. The sample violet, it's O dot, sample violet of O dot 02163 millimeter is measured the dimensional accuracy of the batch ball. So in this example, the error in the estimate results from the combined effect of both manufacturing process error and the measurement error. In the least squares line estimation, a line which can be linear or non-linear is fitted to the data so that the FFE between the data set and the line is minimized. In this case, the line is a model and is represented by more than one parameter. But no, two parameters are needed to represent, namely, straight line, 3 parameters for quadratic function, and so on. Since many algebraic expressions become linear when plotted to a logarithmic scale, a linear straight line fit becomes more accurate when logarithm axes are used. Clearly, linear last square fit is an estimation method which estimates the 2 parameters of an input-output model or process model, the straight line. It fits a given set of data to a straight line such as that the squared error is minimum. In the context of sensing and instrumentation, it is also known as the mean calibration curve. Instrument linearity may be represented by the largest deviation of the input-output data from the least square straight line fit of the data. So least square line, or LSE, comes under the general subject of model identification or system identification. Sometimes you may call it as an experimental model, where a model of no matter static or dynamic is fitted to the data. Essentially, the parameters of the model are estimated, and treatment of estimating the parameters of a dynamic or non-algebraic model is beyond the scope of present treatment. Okay? Consider n pairs of data. You can see x1, y1, x2, y2, and so on up to xn, yn, in which x denotes the independent variable or input variable, and y denotes the dependent variable or output variable of the process or the system that is being identified. Okay? Suppose that the estimated linear regression or linear model is given by this expression y proportional mx times a. M here is the slope. A is the intercept of a line. For the independent variable values x sub I, the dependent variable value on the regression line. Regression line here, mxy plus a. But the measured value of the dependent variable is y sub I. The corresponding error or residual is y sub I minus mx sub I minus a. And hence, the SSE for all the data points look like this expression E here sum for all n with this expression or regression line and square. We have to minimize E with respect to the two parameters. Which parameter? Only M and A. The required conditions are dE over dM is a differential, partial differential. It should be equal to 0. And responding dE over dA should be equal to. By carrying out this differentiation, we get the two expressions here on the bottom for summing. Like, not very, in practical, very, very simple. Dividing these two equations by n and using the definition of sample mean, we get this first expression. I repeat it here in this slide. Solving these two simultaneous equations for m, we obtain equation for m here, for this on the middle. The parameter a does not have to be explicitly expressed here, because we can eliminate a and express the linear regression line as next expression. But note, however, from the y-axis intercept, in case the value of y and x equals 0, and it is given by this equation of the bottom, a proportional y average minus m times x average. So how we define the a? The quality or goodness of an estimate depends on many factors, such as you may see these 5. Accuracy of the data, size of the data set, method of estimation, model used for estimation, and number of estimated parameters. Some useful error statistics that indicate the goodness of a least square error fit are defined next. I remember here SSE. SSE, this is the sum of the squares of error at each data point, with respect to the corresponding point of the best fit. Specifically, as you may see here, it's y sub I is a measured data value. Y sub I as a head is the corresponding value as predicted by the line of the best fit. Okay? A value closer to 0 indicates that the model and the data have a better match or more accurate. In this case, the random error is smaller. Mean square error, MSE, mean square error, and this is adjusted the average value of SSE and given by equation from MSE. M here in this one is the number of coefficients of the fitted cube that are estimated through the curve fitting. The number n minus m is called the residual degrees of freedom. For a line fit, m equals 2. The rationale for this adjusted average should be clear. In particular, when the same number of data points is used to estimate more model coefficients, the estimation accuracy would be lower. A root MSE is this square, R square. So root RMC, it's also called the coefficient of determination. It is at the middle, a root square, coefficient of determination. It is defined, as you may see, expression for R squared here, where Y is the average value of the data point. But SSE represents the deviation of the data from the model. The denominator represents the deviation of the data from its simple average. Generally, the average is not a good model. And it follows that R squared represents how well the data match the model. A value of R squared is closer to 1 is desired since it indicates a better fit of the data with the model curve. And let's look at the bottom one, adjusted R squared. For a given set of data, when the number of coefficients in the fitted curve increases, the accuracy of the estimate decreases in general. This is taken into account in the adjusted R squared, which is defined as this expression for adjusted R squared, and this can see. Where MSE here is the mean square error. I hope you remember, right? And VAR is the simple variance of the data. In the summation of affiliation, we may include a weighting WI for each data value Y sub I. The weight may reflect such a priori consideration as the accuracy and the importance of a particular data value. In the formula given earlier, we have assigned equal weighting to all data values, so W equals 1. Okay? Nice. Next lecture, we will be continuing this topic. And for this moment, I think it's enough. I hope you enjoyed this lecture, and I'm looking forward to see you next time for our final lecture, for lecture number 15. Bye.